What if our moon were another Earth? The first images are almost dreamlike, a second blue planet hung in the night sky, oceans catching starlight, continents showing shadowed relief. From the surface, the sight is overwhelming, a permanent midnight dawn. The rest of the solar system looks unchanged at a glance. The outer planets keep their lanes, and the clockwork of orbits seems intact. That apparent serenity is the first deception. Replace a 0.012 Earth mass moon with a full Earth mass satellite and the tidal physics changes by orders of magnitude. Real tides scale with the companion's mass and fall off with distance cubed. A twin Earth at lunar range would create tidal bulges many tens to hundreds of times larger than those we live with today. Oceans would respond with giant, rapid bulging, vast currents, and powerful vertical mixing that would reach deep waters and redraw global heat flow. Why does that matter? The climate engine depends on how heat moves from equator to pole and from surface to depth. Strong tidal pumping forces cold deep water upward in places that normally carry warm surface water poleward. That upwelling reduces the net poleward heat transport, cooling mid and high latitudes and changing storm tracks. The first effect is subtle, a small decline in mean temperature. But the climate system is full of amplifiers. More ice forms where the ocean cools. Snow and sea ice reflect more sunlight, reducing absorption and pushing the planet further into cooling. What begins as a fraction of a degree becomes a trend. In the simulation, the change is patient. The global mean slides from roughly 7 degrees Celsius downward, year by year. Seasonal rhythms distort. Summers shorten in effectiveness, winters deepen. After about 28 years, the mean approaches -4 degrees Celsius. Maps turn pallid. Coastlines that once teemed with life now carry white rims that never melt. Rivers develop persistent ice cover. Plains that once green are slowly enrobed in frost. The twin Earth itself does not follow the same path in detail. Its surface shows more exposed water and localized extremes. Tidal forcing there drives stronger evaporation and intense localized storms. Its climate flips faster and harder in small regions. Where our planet cools steadily and globally, the satellite's changes are more jagged. Deep floods in one basin, a sudden freeze in another, violent wind patterns between the two siblings. A few additional mechanisms could reinforce this evolution. The heavy satellite alters angular momentum exchanges. Day length and precession can drift, and small changes in axial tilt can redistribute sunlight across latitudes. Baroclinic tides change atmospheric circulation, shifting jet streams and storm tracks into new patterns. All of these effects work together to weaken the planet's capacity to retain and redistribute heat. It is important to note why the simulation looked calm at first. Many planetary simulators, including the one used here, do not simulate full ocean hydrodynamics, baroclinic tides, or the complex feedbacks of ocean circulation. They show orbital motion cleanly but under-resolve the furious, three-dimensional plumbing of real oceans. That absence mutes the immediate spectacle, but not the physics. The slow cooling is a signal that the underlying dynamics are moving heat away from where it keeps the planet temperate. We pause the run and fly over the whitened continents. Ice grows like a slow tide, not a wave. The change is not cinematic in a single frame, it is cumulative. The twin Earth's map flashes with violent local weather as tidal pumping drives upwelling and condensation in some basins. In both bodies, the march toward whiteness continues. If the experiment continued, the most likely long-term lock is a feedback-driven glaciation unless something offsets it permanently. That offset could be sustained tidal heating from internal friction. If strong enough, it can release subsurface heat into the ocean and counteract surface cooling, or a dense greenhouse atmosphere able to trap outgoing infrared. Without such compensations, ice growth increases planetary albedo and the cooling accelerates. This thought experiment is sobering. A new moon as beautiful as a twin Earth reshapes not just the night sky but the fundamental circulation that keeps the planet warm. It teaches a hard truth. Habitability depends on a delicate balance of mass, orbit, and fluid dynamics. A night jewel can be hypnotically beautiful and yet quietly push a world into white.